Okay, so the first topic is on Flink. The uh, the I mean, I'm not going to cover any streaming foundations here. So the course is aimed at slightly um, advanced users of stream computing paradigm, and therefore, let's get started straight away. Um, so the very first topic I want to do is to cover it this way so that we can compare and contrast Flink with the rest of the streaming frameworks that came before it. And looking at it from a use cases perspective, there are three distinct use cases that we can implement using Flink. First one is event-driven applications, and this we are all familiar with. In a traditional application, we see the request coming into the application straight away, and the application is supposed to update, perform some logic, update a database, and return the response to that transaction, all happening in a request response kind of a synchronous fashion. Um, in contrast to that, in event-driven applications, we're talking about events coming in as a stream or written in an immutable event log like Kafka, and the events are unbounded events, which means we know when the start of the events streams happen, but we wouldn't necessarily know when it will end. It's going to continuously come in, and these events will be processed as and when they come in, and you do some application logic on it, um, and um, and then by looking at the events coming in, the sequence of events, the patterns in the events, and so forth, event-driven applications are all about creating some actionable triggers from the events that are coming in. Now, for this to work, the basic capabilities that are needed are mainly state management. So as we keep processing the events, it's important to remember the state of what we are analyzing itself, and the states has to be persistable inherently, so that they can be referred whenever it's needed, or when the platform or when the streaming system goes up and down, there is no loss of data. And using semantics like exact only processing or at least once processing, we're able to continue from where the application left off. So Flink has very excellent state management capabilities, where you can use state backends to persist the state, and it has a great amount of snapshotting, checkpointing capabilities all built inside. It's very matured implementation in Flink. The type of applications that we can implement using event-driven paradigm is anomaly detection, fraud detection, rules-based alerting, some of which we are really familiar with and we are using in Swift. The second use case pattern is the data analytics applications. So in data analytics applications, what we are talking about is this is not on a bounded data, which is basically data available on a warehouse query, but here data keeps coming in. Can you go on mute? There is a little bit of background noise if you're not talking. Okay. So as events keep coming in, we're going to be running some continuous queries. So basically, you can look at data one at a time, or you can look at a windowed amount of data, which is basically per minute, per day kind of windowing. And you are running some logic, or you can actually in Flink you can actually write some SQLs. It's pretty much similar to KStreams where you write KSQL. So you're able to write some SQLs itself, continuously looking at insights from the data. And the output obviously it can be stored in a key value store like Couchbase or Redis or Elasticsearch, as we normally do. And then the state management also has the data inside it. And such mined data, analyzed data, can be used for any ad hoc querying or any live dashboard updates. Right from the KV store, on Flink, there is this feature called queryable state. So from an external application, we can actually query the state data, and we are also able to update and get some results. The use cases of that is pretty much like experiments evaluations. For example, if I'm an e-commerce site and I am making some changes to the website, and I want to see how my customers react to that change, is it positive or negative? Or I'm running a campaign, I would want to find out how my campaign performs during the experimentation phase, where I'm looking at small subset of my customers. I want to see the results of it pretty much in real time, so that I can change, tweak, and improve before I launch to the entire base. So in that kind of scenarios is implemented naturally using this, and Flink has a great amount of support for that. The last one is data pipeline application. So this is like a real-time ETL scenario where data comes in a particular stream, and we do some transformations and then move to another topic or another event log, which can be picked up and then continuously can be transformed until it reaches some kind of a modeled state or a golden record state. Then it finally finds a sink into a data warehouse or somewhere. So the idea is, instead of waiting and doing it in a batch, we do it on a continuously arriving data. So as you see, for all these use cases, some of the most important building blocks are having a notion of event sequence and event times, having a notion of state management, so that it can be fault tolerant. The states can be persisted, and we need some kind of an approach on how do we take the state snapshot when your application is running on hundreds of servers and thousands of parallelized processing elements. So that's the big problem that Flink has solved very nicely. The programming interface is very, very intuitive in implementing such complex logic. And then the notion of event times. So you can either go by the processing time, or you can go by a time which is available in the transaction to make sense of the inherent event sequencing. So all great features, all nicely abstracted and implemented. So that's a quick overview. And what I want to do now is to quickly show you how a simple program in Flink would look like, and then to discuss some advanced topics here. So let me go back to a small application that I wrote just to walk through the features. Now, you can easily create a Flink standard application by using a Maven archetype. And this is basically the POM file where you can actually include the Flink dependencies and any other application dependencies that you want. So it's pretty straightforward. The documentation is very clear. Then the application that I wrote is basically to look at a stream of records, and then it's like a banking transaction, and to look at some kind of a fraud pattern in that sequence of records. So that's a standard application that I wrote. The application itself will look like this. This is the main entry point, and everything starts with creating a streaming execution environment. This is like a handle to your cluster, and then you can write. You can create your source. So basically, a source is something that's going to return a data stream. So data stream is for unbounded streaming data. So the data stream here in this case is a stream of transactions. So transaction is my own class, and it's going to have certain data inside it. So if you look at how this source works is in the source, I'm using the environment that is the streaming environment. I get access to APIs like reading a text file. So I'm going to read, and for every record in the text file, there is a map function that I'm running. So the map API is pretty much like your MapReduce paradigm, where there is an input coming in, which is basically a line in a file. And from that input, I'm creating a transaction record. So a transaction record is going to look at this comma-separated, the file is going to look like this, a comma-separated list of entries. I'm going to break it and save it into a transaction object. So every record will be converted into a transaction object. And that transaction object is basically the tuple that's going to go forward in the stream. So that's like a source. And then you can actually continue to chain what you want to do. So take the transactions, and then I do a key by. So key by is an API that's going to help me to split the data. In Flink, you have all kinds of data shuffling mechanisms, right? So key by is going to, you are going to specify what is the key, and you uses that key to get a hash value, and records falling into the same hash value will be routed to the same processing element downstream. So that's basically to consistently route the data with the same hash value to the same processing element. And alternatively, you can have random shuffling. You can have round robins, and you can also write your custom splitting logic. So key by is when the data shuffling happens. And once I shuffle the data, now I'm going to run I'm going to apply a processing logic on it. So that's basically the process method, which has I'm saying use this class to apply the transformation on the data itself. So fraud detector, again, it's going to be basically you just have to override and implement one of this method, process element method, where you get the input, and you will be given a output port, which is basically a collector, into which you will be writing your transformed tuple. It's pretty much similar to any basic streaming environment. So in this case, it is basically creating an alert record and then writing the alert record into the collector. Every incoming record coming in will be converted into an alert, and it will be written into the collector. So no data getting lost. All tuples will be sent as an alert. This is basically just to show how things work here. So, and then I take this data stream, which is basically whatever I showed, and attach a sink to it, which is an alert sink. And alert sink is very simply going to be logging it, just log it onto the console. That's it. Very straightforward. One-on-one, every record comes in, will become an alert. So it's a very basic scenario. So such an application, I'll be able to compile it quickly. So while this is compiling using the Maven command, what I will do is I'm going to start my Flink cluster. So Flink, this is not a production grade deployment. This is basically using the it's what's called the standalone cluster. So this is running on my local machine. So it's going to have it's going to start up the Flink execution environment. It's starting up now. And okay, so I compiled this application also. So as a jumpstart, Flink gives you a console using which you can manage it. So you can go into 8081 where the web console is deployed. So here is the cluster that I just started on my local host. It has a job manager. It has one task manager. We will see what these things are. And here is how I can deploy an application. So what I can do is I'll go in. This is the freshly compiled application. I'm going to select that and submit it into the deployment environment. I can choose that so that I can mention parallelism. So this parallelism is overall default parallelism. So I just leave it as default for now, and I'm going to submit this. So once I submit it, it's kind of showing me the DAG, the application graph. So I have a source, and then here is the part where I'm splitting the record and I'm running my custom transformation, and then I'm sending it to sync. So just 3 stages in the code. And here you can see that the application started and finished because it's like reading from a file. The file got processed, and then the application says it's finished. So if I look at any of these tasks, I can look at the task manager, select the log, and in the log, because I'm expecting that the application is basically writing every record as an alert. So you see that all the alert logs are coming in, which means the application is actually processing my data. This is a very basic demonstration of it. Now, slightly advanced version of it. I just want to introduce certain things at a very high level, then we can go back to our discussion. Is that suppose if I want to introduce a little bit of logic, not every transaction coming in is actually a fraud. A fraud transaction has a specific sequence in this case. For example, if there is a very low transaction value, which is less than $1, and then immediately if a very high transaction comes in, which means this is a fraud. But here, you see that it is not very high, it is very low, it's medium, and this is very high, but this is not a fraud scenario. So anything that is extremely high appearing right after the extremely low transaction is a fraud. And then these two transactions has to happen within less than a minute also. So only then it's a fraud. So you can see now that the system application now has to remember the state. So if it's been processing data, if it has encountered something very low, it must remember it in the state so that when the next transaction comes in, you can compare and sense it's fraud. It should also remember the time. Is it within the time or not? If this comes in more than a minute, it should clear off this flag that there is a low transaction. So that's a bit of a logic. And which means we need to talk about state management in Flink. So I have coded that also. Just give a quick walkthrough of what that is going to look like. Okay. Just block this implementation of the process element and open up this. Okay. So in state management in Flink, like I said, the programming experience is very, very smooth and beautiful. Basically, you need to tell Flink what the state is. So which means you have to create a descriptor to tell Flink that this is how you can see the state information. Basically, my state information has a key, and it's going to have some value. So in this case, I'm going to maintain a value which is a flag actually, which is a Boolean flag. So with this, Flink understands that I'm going to save one of the state values, which will be called as flag, and the state value itself is going to be a Boolean. And then I'm also going to store the timestamp. So I will say that in this case, the name is time state, and the type is basically the long representation of the time. So I will tell Flink that this is my descriptor, and then I register my descriptors into Flink, and Flink knows how to where my state is. And then as part of the logic, I can actually look at the incoming transaction, and if it is extremely small, in this case, I'm going to immediately set my state to true. So if you look at it in the state here, I am not even representing the actual unique key of whether it's a customer ID, MSSDN. I'm not saying any of that. Why? Because the abstraction here says that this particular class is actually a keyed process function, which means Flink knows what the key is. So if you go back to our original key by way of splitting, I have specified what the key is. Therefore, Flink knows what the key is. And therefore, every time when I am saving the state, I don't have to say what the key is. Flink knows the key of the incoming record, and it manages the internal writing using that particular key. All I have to say is to, set this case as true for that particular transaction ID. And then I'm registering a timer here to say that this is, register my timer. Once again, the timer state, I already described what it is, and I'm registering the timer here also. Suppose if the incoming record is of large value, it's going to now, it's going to create an alert, and immediately clean up my, because now we have detected the alert condition, so I can clear off my all the state that I have saved. I don't need to do that anymore. So that's a simple idea here. Okay. Right. So basically, I'm checking the last transaction itself. From the state, I'm retrieving the last transaction. I know that the flag was already set, which means the previous transaction that I encountered was very small, and then the current one is large, which is basically falling into my scenario. So some simple logic such as that. Anyway, I'm not going to take some time to run this. If I run, it's going to work also. Just want to introduce some very high-level state management concepts before we jump off from here. Okay, I hope so far okay, right? If there's anything you can stop at this stage.
Yeah, I want to ask a few things, Raja. So can you go back to the code which you were
Sure.
showing? So over here, you referred the last record state, right? But how we are telling Flink to get the last record flag state? Uh, is it just whenever you are referring first time, it will take the last record states directly, or are you
Oh,
specifying somewhere specifically?
okay. That's a piece of logic here. Whenever I encounter a small transaction, I save that I encountered a small transaction in the state, and
Yeah.
and whenever I'm encountering the next transaction, I am referring to the state. In my state, did I encounter a small record? And then I know that this is a lost saved state basically. That's what it
Okay.
means.
Yeah. So
Okay,
whenever you are
and
referring the state, it is the last save state.
yeah, that's right. So suppose if I'm encountering a medium transaction right after the small one, right? And basically it
Mhm.
goes into this part to clean up the state, which means the state itself won't exist.
Okay. Yeah.
Okay,
So, and how you are managing the timer? Like for your example, you were saying that it's like one
right.
minute.
That's
So,
right. So the moment I register the timer here, Flink framework will call me back when the timer expires. So I'm sitting, wait for 1 minute. When I register my timer, wait for 1 minute. And after 1 minute, Flink is going to call me back. And when I'm getting the call back, I will clear everything within after that 1 minute. So which means every 1 minute I keep resetting my state. And within that 1 minute only, this has to happen. So therefore that's a callback that I have to implement.
okay, understood. So it's
Rajat,
if I refer back to streams, it is like on punctuation or something like that. Whenever that comes, you
Mm.
do something specific like that. There is a timer trigger, a timer kind of call is coming. Whenever that timer
Yeah,
expiring, the call comes and you do something about it.
that's right. So in Sift, we have a lot of requirements for this also, which we custom implemented it by ourselves. Now
Yeah.
you can see that Flink framework is natively supporting all these capabilities.
Yeah, so that is good. One more last question. When you are creating descriptors, can you go to that section where
Mm.
you are deciding? Yeah.
Mm.
So just to understand this clearly in my mind, uh, is it kind of every key is if I just try to map it to the database,
Mm.
every key is a record and every descriptor is a column, and that will keep getting created whenever you set these values, and whenever you want to refer back you can refer back, or it's just a single value you are saving every time for full scope of the program when
Yeah.
it is running.
No, the state is completely up to you. It can be a JSON object. It can be a complex Java object. It can be composite or it can be a single data point. It's completely up to you. But you should tell Flink what it is. What is the
Yeah,
type of that state?
yeah, I understand,
So
but let's say I created four descriptors. So whenever in the whole scope of the program there will be these four descriptor will store only one value, or it's a time series data which it's saving somehow. I just want to understand that. Let's say there are four record
okay,
came in all four of them. You saved the state of flag and the timer state also. Now, will there be four values kept for me so that I can query it later, or it's just last
it's up to you.
state?
It's up to you again. It's up to you again. So the idea here is okay. Let's take an example. In Swift, we have data coming in, and we keep computing indicators based on every record that's coming in. So basically, uh, that object is what we are talking about as Swift here. It's a composite object. Whether you want to maintain it inside that object, you want to keep a time series, or you want to keep consolidated one value, it's completely up to you.
Okay, so this is something like a class, and just for a layman kind of,
Mm,
it's a class
This is
variable,
an object.
and
Yeah.
yeah, okay,
Think of it like an object. It's completely up to you to put what you want to update inside it. But when does this state gets persisted? So let's look at the state management in that topic. I will tell you, because so far this state is going to be maintained in memory within your application in the heap.
yeah,
But that state can get lost if the process goes down. So Flink has a way of persisting that state using a checkpointing mechanism, which we will see in the next discussion.
Sure. Okay, that's it from my side.
A couple of things actually from my side. Sorry, Jaideep, you want to say something else?
No, that's it.
Okay. A couple of things, Raja. When you were showing us that, can you go to the whiteboarding, Raja? Yeah. Here, when you're talking about the transactions, right? These are transaction corresponding to a particular subscriber or probably corresponding to a particular account,
ID,
right?
Identifier. Yeah, that's right.
But how are we making sure that we are the last updated field is corresponding to the same account ID, for example? There could be many tangled things, right, coming in.
Very good point, Raji. So here is the notion of, I just mentioned it, but let me go into a little bit of details here. So you talk about keyed process function, right? This is the base class using which I'm implementing my processor. So a keyed processor basically receives, basically understands the key, the actual object, that is the incoming tuple or incoming object, and what it is supposed to produce. So which means the key is already recognized by Flink framework. And when you are chaining your processing here, when you construct a graph, you are saying that take this source data and you split by key, and you are already telling Flink what the key is. So the key in this case is account ID. So which means the Flink framework already knows what the key is. So in this transaction, okay, let's look at what a transaction is just to be sure of what's inside here. So the transaction consists of the account ID, timestamp, and the amount, of which I have already declared account ID is the key. I have already declared to Flink. So Flink knows this now, and then because of that, every time the state is written, I don't have to specifically say the key. The framework knows the key. So all I have to do is to update the state, and I only have to give the state value. But Flink knows the key, and it will manage the key and the value by itself. Similarly, when I'm reading it also, when I say flag state.value, it knows the key of the current transaction which is coming in, and it will retrieve the correct value for that key.
Okay, if there are transactions corresponding to, say, account 1, account 2, and account 3 coming in one after the other, and again, if the fourth record is account 1, then it goes back and gets the last updated value of account 1 and then updates it based on that, is it?
Absolutely.
Or it may be holding in memory, for example. Basically.
Yeah. So initially it's held in. Okay. Every time I maintain a state, by default states are maintained in the heap, and then it gets persisted at the regular checkpointing intervals. So which means when the transaction comes in, incoming transaction comes in, because it knows the key, so it's able to get the saved value for that key, the state value for that key. This value API does that inherently.
Okay. One more thing, Raja. Can we go back to the whiteboard? The first screen in this, the architecture you were showing. Yeah, in this you mentioned that you could run SQL queries also on top of it, right? So when you say that means you're actually running the SQL queries on top of a window, right? The data of a particular window, not the entire persistent storage, is it?
By right, the native window support is predefined, but you can actually write a custom window function, and then you are running your query on it. So it's completely up to you. There is no limitation on how much your SQL will scan.
Okay, but I'm just thinking from the latency point of view, because when we call it as a event log, then latency comes into picture, right? When we are talking about a huge SQL query.
Yeah, that's right. Yeah, so that's a design consideration one has to make. If you are able to run the query on per minute window, and you are updating it somewhere on a key value store, or you are updating it on a state, basically you have reduced the data. Maybe you are looking at 10,000 TPS, but if you do a minute window, you have completely reduced the number of records. So you can actually keep the data reduced even in a minute processing. You can do that, And then you can further query either the key value store or the state or using another external process, and you're able to get the aggregates that you want. So again, that's just a design consideration. Flink doesn't restrict you in any way there.
Okay, thank you.
Akash, you had some?
No, I was going to ask the same question about the states being maintained at the account level. The first question Rajiv asked.
Right. Yeah, I think that's the part where you have to understand that the framework is abstracting a lot from us. So it looks a little bit unnatural for people like us who were handling it by ourselves manually in the past. But it is a great feature. You don't have to worry about all that. As long as it's a keyed process and you have identified a key, you just forget about it and you write your program as if you are doing it normally. The rest is taken care. Okay, so in the interest of time, let's keep moving forward. So I'm going to touch on the runtime architecture of Flink to see how it really works, whatever I ran. So similar to any other framework, Flink has the notion of job managers and task managers, and then it runs on a cluster provider, a resource manager like Mesos or Yarn, or the latest version also supports Kubernetes. So typically what happens is you have a code like what I had just now. We compiled the code, and then I submitted the code through the front-end UI application. So that's like a client. So when I'm submitting my client application, the client application basically looks at my code, and it's able to create a DAG by looking at the main function, which has the DAG in it. So the DAG gets submitted to the job manager. The job manager, like any other streaming framework, it has a scheduler, and in Flink, it has checkpoints coordinator also runs on the job manager. So Flink looks at the job manager looks at the graph, and it's going to do something smart here. So let's take an example like this. So I have a source, and I do a simple transformation on the source data. Then I'm shuffling the data using a key by function. I apply a window on it, let's say 1 minute or 1 hour window. And on that, I'm applying some aggregation function on it. And finally, I'm writing data into the sink. So in this kind of a typical flow, what happens here is the only part where I have to shuffle the data, which means whenever data comes in, and the map function which is going to run on the data can actually be fused into one particular task. You don't have to really go across processes, run the source in one process and map in another process and do inter-process communication or inter-server communication. That's going to be ineffective. So Flink is smart enough to understand this, and it's going to fuse these two things. For example, in this case, the source and the map will be fused into one particular task. The key by, which is going to be shuffling the data. So this arrow, let's say, it indicates the shuffling of the data. And when it shuffles, because the shuffling is involved, the rest of the processing will have to be a separate task. And in that task, if you look at it, there is window, you can actually hold the data, and then you can apply transformation on that data. This also can be fused into one single task. You don't have to really run them across multiple processes. So it's going to fuse that together. It's called chaining in Flink's terminology. And when you write to sink, here you have to run the sink as a separate process because there's only one sink usually now. Now all of these have to pass the data to that one sink. It's kind of a reduced paradigm here. So that's going to run on another task like this. So this is basically a logical view of the DAG. But what's going to happen to when we introduce parallelism here? So let's say I have a parallelism of 2. Let me just start writing here. So my parallelism is 2. So what's going to happen is this particular part. Okay, I'm going to now do the runtime view of it. So there's going to be 2 instances of this. And the data needs to be shuffled now. So it's going to be data from here can go into that as well as sorry. So I'm going to have data coming in this way and this way also. And then finally, I will have this particular sink to which data will flow from here and here like this. So this is pretty much in a parallelism of two. I can actually set parallelism for individual tasks, but overall global parallelism is going to work in this way here. And after that, if you notice, this is you can name, you can kind of give a task ID 1, 2, 3, and 4, and 5 here. And then if you look at your runtime environment where we have configured task managers. So task managers is more like the JVM process, and every task manager is going to have task slots. Task slots are threads inside the JVM. So that's the simple way to look at it. So at the time of deployment, what the job manager is going to do is, this is basically going to be the runtime view, and it's going to be saying that, okay, run the task 1 here, 2 here, 3 here, 4 here, and 5 here, some way of allocating based on the load and various other factors. So that's how the runtime is going to work. Straightforward? Okay.
Yep.
Okay, cool.
Now, what are these slots? I mean, these slots are. Does it represent?
Threads,
okay.
They're basically threads in the JVM.
Okay.
So Raja, are these all the functions which are available as a basic functions of Flink, or so that it knows which one to be merged together and which one cannot be merged together, or it's just an example?
Yeah, that's right. No, that's right, Jerry. All these APIs, map, keyby, shuffle, and it's all Flink APIs using which we'll be writing the application itself. And Flink knows which of these involves data shuffling, which means data shuffling means it's a separate stage. So Flink knows all this. So you are going to use Flink APIs to stitch the entire bag.
Okay, so one more question. Let's say I have multiple aggregation or apply function which you're calling, right? Let's say I have chain of apply functions which I want to implement, and if there are 5, 10, let's say for example, apply functions I'm using, will it merge all of them together to make one task?
I think there is a default way to look at it. If you are applying, I mean, the best is to write them as one apply. But if you say apply this and then on the output apply this, as long as there is no data shuffling involved, it is going to be implemented as a single task. That's the most efficient way of deploying it. Yeah.
Okay. Okay. Means I'm just thinking that, let's say if there is something very heavy happening in that function, in quite a few functions, and if we merge all of them and put into one task slot, will it be able to perform at a speed in a particular server, let's say? I'm just thinking from that point of view, operational aspect.
I understand. But you will use the parallelism. So although one single task is heavy, if you increase the parallelism to 100, which is going to be running in different threads, you will be able to manage that.
Okay, this shuffling will help in that case, like the data distribution and then the parallelism.
Okay. All right, great stuff. So,
Raja, just one question. Parallelism is like in this case, as I understand, is by the virtue of having multiple threads within the same JVM. So there would be a limit to how much you can parallelize these applications.
Oh, no, not really. So okay. When you say parallelism, you are going to say how many subtasks. Okay, for example, this is one task, but if you look at them, right, these are the instances of different tasks, right? So parallelism here talks about multiple task managers. This could be you could be having hundreds of servers, each of them having multiple JV task managers inside it. So you are actually going to put them across these servers, right? So
okay.
So if you say your JVM is going to have only 5 slots, let's say if you fixed it, which means that's all that JVM will handle, but then there will be horizontal scaling after that.
Okay.
Raja, does this job manager also understand the resource availability of the servers and all that?
Absolutely. That's how the job manager works with Mesos, Yarn, and Kubernetes. So it knows the task managers. It knows because of the cluster managers interaction, it knows how many physical servers are there. It knows how they're utilized. So it's able to schedule from that perspective. So it's a usual scheduler that's going in there.
Okay.
I have one question, Raja.
Yeah.
Okay, I'm just bringing in the streams concept here. They've got the concept of P's, right? So if we just merge some of the operators into some P's, the data transfer between them is through function calls. How does it happen over here? Question one, and second is, are there alternatives?
So if you fuse them,
Is it?
Sharad,
Yeah, yeah, yeah.
once you have fused them, it's actually a function call.
Okay.
So that's the whole idea of increasing the efficiency from there. Yep. Okay. Okay. So the idea here is Flink is smart enough to understand what needs to be fused. We don't have to really make a decision on that. So that's where it is. Okay. Now let's move to the state management. Basically, this is some topic that a lot of questions came about, and we discussed it. So I can be slightly quicker here. So why do we need state? As we discussed in our example, there is a sequence of events I'm looking at, looking for a specific pattern. That means I need to go back to what my state was previously. So I don't have to really manage it by myself. Flink frameworks have it in memory for me and saved it also in a persistent store. So I can actually refer back to that, to that information. If I'm aggregating, and then I need to know the last aggregated value, which is again a state function. In a machine learning training, I need to remember the parameter values of the model that is trained so far, so that with the new data I can continue on it. So that becomes a state for me. In historic event processing, back to Rajiv's question, if I'm running a SQL on a window, I need to keep the data for that window so that I can run the query. So that's where state comes into play. And as we discussed, let's say I have two sources and I am doing a key by shuffling up the data. So all data with keys ABC goes into one of the processing elements. All data with DEF goes into another processing element. Let's say I have the shuffler done in this way. So when the data comes in here, keys ABC will always come in here. So in the state management, I have A, and its state will be saved by Flink automatically. B and the corresponding state will be saved automatically. So this could be the customer ID, account ID, whichever key that I have configured in the code. So that's something that we saw previously also. And every time, question?
It's something like what we do in Swift, right? We are making a cache and maintaining all the accounts in that with the JSON document along with that. So that can be done directly through descriptors. We don't have to maintain any hash or anything like that.
Absolutely, that's all it is. Yeah. So this is we don't have to programmatically do it, and the framework is going to take care of that. And whenever the states needs to be checkpointed, and this is what Flink is going to write into a persistent store, which we will see how that's going to work. So here's the idea of like I discussed, the important problem here is to solve this checkpointing method so that we can implement exactly one's semantics, or at least one. So Flink has a technique called ABS, which is asynchronous barrier snapshotting technique. And very quickly, and it's very easy to understand this. So very quickly, the way it works is, so let's say in this simple application, I have data coming in from two Kafka topics. Okay. So this is my first topic, and this is my second topic. And I have the Kafka source. So this is what Flink has provided us, and what it calls the connectors. So let's say this is Kafka connector, using which I am actually reading data, and this data is what is getting into my processing here. So let's say everything is running and the state is all managed within the operator. So the state is in memory here. It's all good. So what's going to happen now is, let's say there is a time comes where the snapshotting needs to be introduced. And if you remember our architecture, job manager has a checkpoints coordinator. So here is the job manager, which is actually going to say, that, okay, it's time to checkpoint the data, and just go for it. So it's going to initiate the checkpointing request to these sources. Now, the sources have it's been continuously reading data 1, 2, 3, 4, 5, 6, and here is A, B, C, D, E. So it's been reading data. Now, in this ABS, asynchronous barrier snapshotting, the technique is there's going to be a special tuple called a barrier, which the source is going to introduce. So the moment this request comes in, now the connector is going to say, okay, my snapshotting, everything that is processed before record 1 is what my barrier is. And here for the second one, everything up to D, this is where the barrier is, right? So let me just use a different color for it. So what the sources will tell the JVM is that, okay, this is the Kafka offset, which is going to be the marker for me, the last processed before the checkpointing is supposed to happen. So which means the job manager will now remember that, in this topic 1 and this is topic 2. So topic 1, the checkpointing is happen before that particular offset, and then topic 2, the checkpointing is going to happen before this particular tuple here. Right? So it remembers the Kafka offset now, and this particular barrier now, this special tuple goes downstream here into the whole DAG. It travels. So here is an operator. This is an operator. Let's say it receives that barrier, which means it is not going to process it anymore until the state is persistent. So it will hold this here. Now here in the second topic, there is a lot of data coming in, but the barrier hasn't reached. So for this exactly one semantics, the operator has to now process everything and wait for the alignment of this barrier to come. Okay. So here the barrier has come. So which means barrier has reached for both incoming routes. And at that time, it can actually take the state and then snapshot that state, save it into the disk basically. So here you can actually configure a state backend. Usually it's RocksDB, which has a very efficient mechanism to write the data to the disk. And then the state gets saved in that way. So once the state gets saved, everything can continue. But what happens is this operator is going to now introduce the barrier to the next operator downstream, so that the same thing will happen in that next operator also. So which is consistently for that particular source offset, everything is processed before that particular source offset will be a consistent state across the whole graph, and every operator will save that state at that point in time. So this is why when there is a crash and you have to play back from the crash, now you can take the state and you know that the source has to be the last processed data in the source is like this. You can start to replay the data from that point onwards, and the state exactly matches the state of the application at that point in time, and then you can go ahead with that. Okay, so far okay. This is something that's greatly implemented.
So Raja, this is what you explained with the Kafka, but let's say there is a file source. So is it saving the whole record till what we have processed, or it's just a key hash value or something like that it is saving?
With the file, okay. So basically for this exactly one semantics to work, you need to have your event source, which is like Kafka, Kinesis data streams. It has to be one of those which can be replayed at any specific point in time. So which means file sources, it's going to be completely difficult to implement that, but it's not impossible. But the whole thing is that the connectors here, right? That's what the smartness is, because when the JM starts the snapshotting, it's going to the sources only. So Kafka connector, Kinesis connector, and a whole list of connectors that's available in Flink knows how to save the offsets and then to read. So it needs two things. One is the connectors that can work with the JM based on the contract, and a source which can also go back in time and start to stream from any offset. So only such sources and such connectors can be naturally take part in this dynamics.
Understood. The other question which I had is if you see in the flow in the second part of it, what it is doing that until both of the barrier has not arrived from the source, it is not doing the backend synchronization, is it? So I mean, I just want to
Yes.
understand if it is for all the input stream until the barrier has arrived, it will just hold and it will not do any of those, right? It will not process the data from the barrier, which for whichever stream the barrier has come, and for the ones the barrier did not come, it will keep processing, and when all the barriers are there, then only it will write the state.
That's right. Yeah.
And when it is done with its own job, it will forward the barrier to the next downstream.
Absolutely.
And it will start working again.
Yeah. So it's possible there could be some back pressure handling that has to happen here, but Flink manages that.
Yeah.
But Raja, in this case, right, since the checkpointing is happening after every frequency, not at the every record level, there is how does it maintain the exactly one semantics here?
Okay. So basically, yeah, it is a scheduled activity, and you can configure how frequently you want to snapshot. If you snapshot too frequently, it has an impact of too many checkpoints to be written. It's going to slow down the latency. So it's up to us to tune at what frequency we want the checkpointing. But at least what we know is when the checkpoint is initiated at that particular offset, all the operators have saved that state consistently for every record before this. So basically, the barrier means anything before the barrier is completely processed all the way to the end, all the way to the sync. Okay, I forgot to mention that when the last sync finished the barrier, it's going to tell the job manager that this is when the snapshotting is completed. So everything is gracefully understood from that point onwards. So it's a guarantee that everything that is before the barrier from every source is completely processed. Now, when the recovery happens, that means when your state comes back, you are exactly at the barrier point. And then you will be able to replay from here onwards. So that's where the exactly one's semantics coming in.
So Raja, until the last operator has not written the state, the data will not flow, is it, from the source?
No, will flow. As soon as any operator finished its snapshotting, it will continue to send data out. So each of the downstream graph, they're all writing. So for example, it's like this. Let's say my graph is like this. So obviously this is my source. So he will write the checkpoint first by himself, and then the barrier reaches here, and then they are going to write their states, and then the barrier is forwarded. He's going to write the state. But as he is forwarding, he can actually continue to process the data. So there will be, once he processes the data, there will be a lot of tuples going in here, but the barrier is already here, right? Yeah. So which means processing never stops. It goes. That's why it's asynchronous barrier snapshotting.
So once the barrier is assigned by the JM, the full checkpointing is complete only after the last operator has written, right? Until that has happened, it will think that the data is not processed completely, right?
Yeah, but
because for a record to be processed, let's say there are 5 operators in between, and all 5 have to finish their job, and then only I can think that okay, this record scope is finished. If that has not happened, I need to reprocess this record again.
Well, okay, so here is the thing, right? So yes, you are right, but you don't have to really stop it, which means the snapshot that is being taken already represent that for that operator, that snapshot is valid. Therefore, when every operator finishes, all the 5 finishes, you have a consistent snapshot. But somewhere, if there is a failure, which means your only valid snapshot is of the previous snapshot. So that's okay.
So I think in a way it is better if I understood correctly. Let's say before the last operator job went down, it will take the data from the previous operator
Previous snapshot
checkpoint.
to continue.
Uh,
Absolutely.
it will not take from
Which
the
is why,
start or anything from the previous one only. Okay.
yeah, which is why you don't have to wait until everybody has written the snapshot.
Raja, just reiterating the same thing actually. If we consider this begin alignment diagram that you have, right? Say this operator has processed XYZ records and the barrier has not yet reached. And if this operator goes down, here we are actually losing the records, right? So when it comes
you are
back,
not, because so when it goes down and when you come back, you are going to play it from the previous snapshot, which means XYZ will anyway come back again.
Okay.
But since you retrieve the state.
Okay. When you say output buffers, those are output buffers of the current operator. They have not actually gone to the input buffers of the next operator, right? Is that correct?
It would go. It would go. Once you put it onto the buffer, it's continued to go anyway.
Okay. In that case, when this operator goes down and comes back up, it will reread XYZ records again and it will send into the of the next operator, right?
No, it won't read it. It won't read. It's only the state that is brought back. So ZYX is produced by the operator because of the input that is coming in, right? So which means when the same input comes back during recovery, it will reproduce Z, Y, and X again. So you only have to retrieve the state and then play back from the previous checkpoint so that it will continue.
Yeah, I think Rajiv, obviously between every checkpointing time, if something is happening, obviously that cannot be brought back.
Yes, or if the operator is maintaining its state at every record level, is that what you are trying to say, Raja? If this operator is maintaining the state at every record level, that Z is processed, and if it goes down, it will bring back this state, is it?
No, you need to look at it from the source, right? So your checkpointing is not per record; it's based on your configured interval. Now, when you play your record from the last processed record onwards, it will again, so for example, when okay, how do I explain this? So you have a state, and the state is actually a completed transformed value of everything that you are analyzing until that checkpoint was taken, right? So when you retrieve the state, which means your application has retrieved the state until the previous checkpoint interval, and you are going to actually play from the source. You're going to play it again. So therefore, you have you just continue, and there is absolutely no data loss. There is absolutely no integrity of your data itself. So anything that is produced in between here, it doesn't matter really. All you have to do is to persist the state.
This is true if we think that frequency of checkpointing is as small as every record. This is absolutely true in that case, Anita.
No, not at all. Not at all. That doesn't matter actually. See, Kafka, you just have to know when is the last processed record in Kafka, and so you put a marker that I processed until this point in time. Let's take a simple case, one particular topic only, one particular source only. So you know that when you introduce a checkpoint at this stage, anything before this, you have to completely process it, and then you take a snapshot. That's the whole idea here, right? So you might have 10 records here that went into the system. So those 10 records are processed by this guy, and then he produced an output. The output that is produced because of the 10 records go to the next guy, and he takes a snapshot from it. Yes, everybody has taken a snapshot, which means the system is consistent until this point in time. And when you recover, you recover that state, and then you start to play from this point onwards. It's perfect.
No, Raja, let's say if we think these three circles as three operators, let's say first one got 3 input and generated one output, right? But the checkpointing did not have complete in the second operator as of now, and the job went down. for the first operator, it will not read again, right? Because it has already generated its data and it's checkpointed also.
No, it won't. Okay, so when you recover, you are going to recover from the previously saved state, and you are going to play all those records again.
No, but we discussed previously that the operator will take the data from the previous operator output, right? Not from the source directly, because source then what we mean that until all the operators have checkpointed, the source will not be in the JM, it will not be considered that this record is processed, right? Because one record makes
it's not at that. No, sorry, it's not at the record level. Okay, let's properly write it, because it's a very important concept to understand. So let's take a case of there are 3 operators, and then my data. Let's say I have 0, 1, 2, 3, 4, 5, 6. So when everything starts, so this is my data here. So let's say I'm processing record 0, 1, and 2. So I have processed 0, 1, and 2 here. I have created a record called X. So X is what I'm sending here. And then this X is transformed and I send Y here. So at this stage, the JM says take a snapshot. So what's going to happen is, so here is the marker. A marker is placed here, and then because of that marker, so I have processed 0, 1, and 2 here. So I'm going to be recording my state here. And then when I pass X, right? When I pass X from here, because I process 0, 1, and 2, I'll introduce a marker here and then pass the X here. So once I process my X, because I received the marker, so the marker is already here, I'm going to take a snapshot here. And then when I produce Y, I'm going to send a marker after Y also. So here I processed Y and the marker is arrived. I'm going to take a snapshot here. So let's not worry about asynchronous for now. Let's assume that this is all synchronous one by one. So which means until this point in time, everything is, my states are all perfect. Okay. So I'm continuing to process now, let us say 3 and 4, and then the whole system went down. So I'm now pushing 3, 4.
Just want to hold you here. Let's say before the second operator emits Y and the checkpointing is done, the system is down. But X has done the checkpointing.
X has done the checkpointing, no problem. So what's going to happen is, because the job manager did not receive all the way to the sync, the job manager did not receive the checkpointing is completed, which means these checkpoints are invalidated. They're not there anymore. They're wiped
I think
off.
previously one question I asked, and I think I was not able to communicate properly. In the previous question I asked, when saying that let's say the job went down after processing of X, if Y is processing again, it will take the data from the previous X snapshot, because that's the one it is generated, right? But that is not the case. Everything is invalid until this last operator has given the signal to the JM that I have completed my checkpointing also. Until that is done, no checkpoint is valid.
Yeah, no checkpoint is valid. All the checkpointing can happen asynchronously until the last guy has said that none of these are valid anymore. Once he finishes it, then it's registered as a valid checkpoint. Valid checkpoint completion.
Then only it makes sense now.
Okay, it's clear for Rajiv.
Does this answer to you also?
Sorry, me, right? Sorry, I got dropped off. I'll look at the recording later. Sorry.
Okay, no worries. All right. So again, in the interest of time, let's quickly go to the last topic. So far, I find some of these advanced patterns pretty interesting in Flink. I'll just touch upon 2 of these advanced patterns, which we keep searching for in our own implementations also. Number 1 is called dynamic splitting. So imagine a case of a record coming in. There's only one entity that we're analyzing, which is basically the customer. So we have a key by transaction, and we can say the key is customer ID, MSSTN, or whichever it is, and then key by can split consistently. So same customer's record goes into the same downstream processor, and everything is fine. But suppose we also want to analyze based on, let us say, the location, because location data comes as part of the input. So we want to analyze that people in Singapore, a specific behavior pattern that we want to analyze. And we also may have things like, let's say, whether it's an IDD call or not. So I want to analyze IDD country. So I want to, aggregate calls made to Dubai, calls made to Australia at that level also. So suddenly there is a notion of multiple different entities that I want to analyze. And therefore, my splitter now has to recognize these multiple different entities and their own IDs and split accordingly also. This is one of the biggest problems that we had in the past. So Flink's way of handling this is a problem description clear, I hope. So Flink's way of handling this is that actually now you can, this particular source is here. So one of the ways I can do this is to introduce a new custom process here. And then I can have my key by, and then this can actually go into downstream here. So what the newly introduced process is going to do is going to now augment or rather split the incoming data itself and add some extra information to it. So let's say my data itself is here. This is basically my record. So traditionally, this particular process can look at the data and then add a new key called customer ID, and then I'll just write it clearly. Okay, so let's say I'll just expand it here. Customer ID is newly added, and then the rest of the data remains here. And now I also want to split by this, right? So I can split by location ID, which is in fact it's going to be the actual value followed by the same data, and then IDD country as a key. So this could be Dubai or any country that's identified, and then the rest of the data can also be there. So basically, I am now one input record coming in. I'm going to now replicate this record like this based on the different keys here. So here is key 1, here is key 2, here is key 3. I split it like this. And then when the key by functionality, you can specify what the keys are. So you are able to write some dynamic logic here to say that the key is identified by this, and then use that to do the splitting. So with that, now I'm going to have my data going in multiple directions. Suppose if this first key is the customer ID, so based on customer ID, it will do my this particular record will actually go to one of these places. And this particular record is based on location ID. So again, by way of hashing, this particular record may go somewhere here, and the third one will go here. So it's going to be consistently splitting my data because I have a way of now, it's a way of duplicating the incoming record based on multiple keys, and using the key by declaration, it's going to further send my data consistently to different places. So in the processor, we can have a way of identifying that incoming data, or this data is belonging to a location entity, and you can actually analyze based on whatever you want to analyze for locations or IDD countries. You can take care of it in this particular process here. So it beautifully solves one of the biggest challenges that we had in the past. I hope that's clear enough.
Yeah.
Yeah. And then the second important pattern, which I want to touch upon here, is basically the dynamic config updates. So in our implementation, we had our processors that are going in here, and then we need to send a config update. So here is the main processor where the config update has to come in. So we have another stream that's going to be sending the config data to it. Now, in real implementation, because of parallelism, this can be running in multiple parallel tasks, right? Now, how can the config update be sent consistently to all of this? Because in runtime, I can keep increasing or decreasing these tasks. So we wrote our own custom complex implementations for that. Flink's way of solving it is that it introduced some a specific processor function called broadcast stream or broadcast processor. So which means it is going to have a specific stream that is going to come in here. So this is the broadcast processor. I can actually configure in the DAG, I can say that this particular stream that is coming in is the broadcast itself. So this is the broadcast. So it's called broadcast because it's going to be sending the incoming data to all the instances during runtime of that particular task. So which is why it's called the broadcast. So I can write a function extending from the broadcast processor, and then in the DAG I can say I can connect these two by saying that this is the broadcast stream itself. Therefore, this config data keeps coming into me, and I can self-update myself moving forward. So once again, I don't have to really manage the number of instances of the task in runtime and broadcasting the config. So it's all built within the Flink framework. Okay, so that's the last of the pattern. I mean, there are a lot of other topics to discuss. Just want to give a quick overview. I hope this will be helpful for you to explore further all by yourself. The documentation is great, and there is a blog where the brilliant Flink folks write a lot. Yeah, so here it is. So this is a Flink blog where you can see all the advanced patterns, the use cases. Most of the content that I discussed, I took from their documentation itself. So feel free to explore happily.
Okay.
Any questions so far? Do you want to stop here?
I think that's all from my side.
Okay, so there is no questions. Let's stop the recording. JD.